I'm Darcy. I've worked on the JDK for a long time, and tonight for my lightning talk I'll be talking about compatibility in the Java platform. And this is an excellent topic for lightning talk because it's so intrinsically interesting for long periods of time. So in Java there are three basic kinds of compatibility. There's binary, source, and behavioral. Now binary compatibility is defined by chapter 13 of the Java language specification. Very interesting reading. And if you go through this chapter, it explains that if you have an old version of the library, you apply some transformation to get a new version of the library. That transformation is binary compatible if every possible program that linked against the old version of the library continues to link against the new version. If it still links, it's binary compatible. If it doesn't link, it's not. That's it. It's a true-false property. And binary compatibility is important because that's one of the strong guarantees we have involving the JDK itself. Sometimes people use a different definition for binary compatibility to mean something called behavioral compatibility we'll talk about later. However, since the Java language specification is the master of Java terminology, it gets to determine what the term means. So binary compatibility should just be linking. So what about source compatibility? Well, this is not defined in the Java language specification or other documents, and it's more subtle than binary compatibility. This kind of compatibility concerns mapping names in your source files into binary names in the outputted class files. So it's more complicated. So if you do a simple addition like adding a method to a class, if you're malicious and write an adversarial program, you could have a program that, after the fact, linked with or compiled against the first version of the library, failed to compile against the second version because of name clash. So that's too restrictive to talk about source compatibility. We don't want to say that kind of thing makes something source compatible because you would have very little left. So instead, we'll pretend all the names in the Java programs are fully qualified. But even if you do that, you still don't get a true-false property. So in some other contexts, people like to use a color-coded threat system. So we can also use that for source compatibility. So we take a final class here, C, and it has a foo method that takes a double hit. The most severe thing you can do is delete the foo method. So obviously, if you delete foo, that's source incompatible. If your client program used to call the foo method and it's not there, it won't compile anymore. Now this particular change is also binary incompatible. That's one of the changes listed in chapter 13. But there are many other changes that have different gradations of source compatibility or incompatibility that are all binary compatible. The most source compatible thing you can do is a binary preserving source change. So for instance, let's say you add a method bar to class C. All the existing libraries that use C, call the foo method, will compile exactly the same after you add bar. So the binary, the class file you get from the old client will be the same after this change. So that's maximal source compatible. Things start getting a bit more interesting when you start doing overloading. So let's say you add a foo method that instead of taking a double, takes an int. In this case, if you have source code that calls foo with an int, before it would go through numeric promotion and call the double version of foo. Now after you add an int version, by the rules of Java, it calls the int version of foo instead. Now in this case, the double version and int version of foo happen to do exactly the same thing. They have the same semantics, but you get a different class file in each case. The method resolution is different. So that's behaviorally equivalent, although you get a different class file. Something that's a little more subtle is, let's say you add a long overload in addition to the int and the double one. Now, because not all longs are exactly representable as double, your source that used to have a long that would result as a double version, if it results in a new foo version, you'll get different behavior in some cases. So besides getting a different class file, you'll get a class file that does something different at runtime. But everything that compiled against the old version still compiles against the new version, but you get a different class file that does something different. So that's why source compatibility is more subtle. Now behavioral compatibility is even worse, and it's not compatible with lightning talk because it takes too long to talk about. Because potentially your program could depend on timing, or reflection, or even stack traces, properties of the platform that aren't qualified. So we can think of these different kinds of compatibilities defining a three-dimensional space of allowable regions. So when we look about evolving the JDK, smaller releases have a more constrained compatibility region. We don't want to make big compatibility changes in an update release, and we have somewhat more room in a